Hello science fans, welcome to another adventure. Today we're going to go through a bit of graphing review where we're going to convert graphs from one type to the next and then probably to another one afterwards. We'll start off with this graph over here, which is known as a position time graph. Often it's confused with a distance time graph, but remember distances, they only increase, kind of like the odometer in your car, right? No matter if you're driving towards the east or if you're driving towards the west, the odometer keeps on increasing. Position, on the other hand, it's where you are relative to a known reference point. All right, so where X marks a spot, if you're getting closer or further away from that marking. Okay, so when you're trying to find out the velocity on this type of graph here, what you're really doing is that you're measuring the slope of the graph. There is another way of solving this, which is through the world of calculus, and that's probably why you're learning that at the same time in grade 12, so that when you reach first year university, you can see how those two universes intertwine with one another. Okay, but let's just stick with what we know so far from back in grade 11 physics. All right, where to find out the velocity at any given point on a position time graph, we take out our handy dandy ruler, drop it on our piece of paper, and draw a tangent. Okay, I'm going to start off with a tangent at the 1 second mark. I'm just choosing any arbitrary point. And when you draw your tangent, that tangent must go through that point. All right, not like that, all right, but must go through it and touch that point once and only once and not cross through your original curve. Okay, so it should look something like that. And in fact, that looks like a pretty decent tangent. It's not going to be perfect when we do this because we're doing this mechanically, and that's why there's the mathematical way or calculus in solving it. But this will give us the approximate answer. Best thing I can tell you is that whenever you draw your tangent, make sure it touches that point once and only once, and the separation between your tangent and the curve, they're roughly the same on both sides. Not exact, but roughly there, and that's as close as you can get to the right answer. Next thing you're going to do is you're going to measure the rise over the run because that will tell you the slope. Choose points that are far away. The problem about choosing points that are right beside each other is that now you're just subtracting 2.3 from 2.2, which gives you 0.1. All right, and anytime that you have measurements that only have one significant figure, it gets pretty bad. In general, this is not always true, but in general, if you have a measurement that's one significant figure, your errors could be up to 100% off. How did I arrive at that number? Let's say you estimated 2 instead of 1. There you go. You could be up to 100% off from your correct answer just by showing only one digit. Now, if you so happen to show 2 significant figures, then your errors decrease quite a bit. Now you're down to a much more reasonable 10% error, which often is the case, especially in electricity. All right, you don't expect voltages to be constant; they do fluctuate, and 10% ripple is often expected. All right, a 3 significant digit. Hopefully, you see a pattern here that drops your error down to 1%, and that's why I often like to have our measurements showing 3 sig fig, because that means you're only about 1% off from your actual measurement, and that's in general is not noticeable to the human perception. Right. For example, if someone gives you a meter stick, but secretly they chopped off 1 centimeter, would you be any wiser? You probably wouldn't notice the difference. Okay, 1% error as a human beings per se, we won't notice that difference. Instrumentally, we can see the difference, but from our perception, we're not going to notice 1% error. All right. So 3 sig fig in our calculations, it's a good place to start. Okay. And yeah, if you go to like 4 sig fig or even 5 sig fig, your uncertainties dropped to numbers that are just way too refined. All right, where if you need those measurements for some reason, then by all means show it, but it gets to a point where it's impractical to measure. It's like saying that when you're up to, I'm just making it up, but I'm sure six significant figures is probably reasonable, stating the distance between where your toe is and where the fire hydrant is outside your house. Okay, that could be 6 significant figures measured in centimeters. Okay, and how certain are you to the nearest centimeter on that? Every time you measure, you'll get a different answer. All right, so 6 sig fig is kind of extreme. Yeah, stick with 3 or 4 as the most you'd ever show, at least on a test. All right, 3 to 4 sig figs. You don't need to go more than that. Anyways, back to this problem over here. We need to measure the slope, and what points should you choose on this tangent? Realistically, you could choose any point. Just make sure they're at further extremes. Oh no, that was a nice tangent that I just lost. Okay, I'll try this again. That's not a tangent. Sorry about that. Somehow I have a feeling I'm not going to get the same answer as before. Yeah. Okay. The next line, I'm just going to call it quits. Whatever this shows is whatever I'm going to work with, and I'm glad that that's pretty decent representation of a tangent. Okay, you want to choose points that are at their extremes, and it does help to choose points that pass through the cross hairs or of your grid of your graph paper, right? Because in this case over here, we definitely can tell that at this point over here, our time is equal to 0. Sorry, 0. I think 2. Yeah, 0.20 seconds, because we know it's right on the crosshair. And we'll call it T1, and our position at this point over here is at 3.0 meters forwards. How did I know? You always label that in your axes. Okay, so include the unit, and if it's a vector, include the vector symbol there as well. Okay, so that's the first point. Our second point over here, we'll call it time of reference number 2. That's at 2.20 seconds. How did I know this was 0? Because if I had it somewhere over here, I'd probably have to estimate 2.21 seconds. All right. So that's what I mean. You want to choose points that pass through the crosshairs of your graph paper, because you can get much closer to the actual answer. It just helps. D2 is equal to 17.0. Yeah, 17.0 meters. 16, 17, 18. Isn't it 18? 18. Sorry, 18.0 meters. Okay, and if we want to find out the instantaneous velocity, that's equal to the slope of your tangent. Okay, so it's equal to d2 minus d1. That's vectors. Whoops. Meters forwards. Subtract 2 minus t1. Time is scalar. Why is time scalar? Because even though we perceive time moving forwards, we can't measure time moving to the east or to the west. That's why time is scalar, okay? And we can't go backwards in time either, so time is scalar. Position, on the other hand, we can measure it east, west, forwards, backwards. That's a dead giveaway. It's a vector measurement. Okay, so 18.0 meters forwards, subtract 3.0 meters forwards, divided by 2.20 seconds, subtract 0.20 seconds. That gives you 15.0 meters forwards. Remember that there's brackets on top and brackets down below, even though we don't explicitly state it. And we're dividing that by 2.0 seconds. That will give us 7.5 meters per second forwards. Okay, so specifically at 1 second in our adventure over here, the object was moving at 7.5 meters per second forwards. And what I like you to do is I'll clear the screen capture if you need to, and print this out. Measure out the tangents at 2, 3, 4, 5, and I guess try for 6 if you can, or somewhere near 6 seconds. You probably can't, so I don't know, 5.5 seconds. All right. Take those tangents, measure them out, calculate away, and then I'll reveal the extra answers in the next slide. Okay, 5 seconds is plenty of time. Here's the answer. Okay, and as we stated, I was slightly off, but that's what happens when you draw tangents. I got 7.5 meters per second. It should have been at 8 meters per second. All right, so my calculations were not bang on, and that's just the nature of drawing tangents freehand. All right, it doesn't help that my pen isn't perfectly calibrated to the screen either. So yeah, make sure you like, click, and subscribe so that I can get the funding to get a screen that's better calibrated. How about that? All right, and thanks Josh for the screen. I'm still using it to this day. Okay, so yeah, so once you've done your tangents, you would get 8 meters per second at the 1 second mark, 6 meters per second at the 5 second mark, what is that, 4 meters per second at the 3 second mark, and this will be a linear correlation, right? And this linear correlation tells us that the velocity is gradually decreasing as time goes by. All right, and anytime the velocity gradually increases or gradually decreases, we're experiencing something known as uniform acceleration. In this case over here, I know it's tempting to say that's decelerating, which it is, I guess, in real life and using English speak. But according to physicists, we don't like using the term deceleration. Instead, we just simply call this acceleration in the negative direction, or acceleration in the opposite direction. And that's what's happening when you're decelerating, right? Like, for example, if you're in a car and you call a shotgun and a friend's driving, when they step on the accelerator pedal, your body shoots backwards against the seat. And if they see a squirrel on the road and they are animal lovers, they will definitely slam on the brakes and your body will lunge forwards as your car decelerates, right? Because deceleration is acceleration in the opposite direction. Okay, so with this linear correlation over here, you could find out the tangents in all these small points over here. However, that's unnecessary. You'll see that this is a linear correlation, so just measure the slope of this in its entire. Go ahead, calculate that out. Hope that's enough time, and you'll find out that the rate of deceleration of this, in fact, I could probably figure this out, it will be at -2 meters per second. Yeah, and that's the answer that we get. All right, -2 meters per second, or -2 meters per second squared. That's how we call it here in Canada. In the States, they still use the really long-winded feet per second. All right, it takes a long time to say, even though it's still correct. Okay. The more thing I want to mention about is that, you know, whenever you're converting from one graph to the next to the next to the next, all you're doing is you're measuring the tangents of each of the graphs and then transferring the slopes of the tangents to the next graph. Okay, so you start off with your, let me just rewind back. You start off with your position time graph. You do all your tangents everywhere, transfer them over, and now you get a velocity time graph. You measure the tangents of this, and you get an acceleration time graph. And if you measure the tangent of this one over here, you'll notice that it has a slope of 0. What unit is used to describe this? Well, a slope of an acceleration time graph is known as a jerk time graph, or if you're British, a jolt time graph. Okay, and yes, you could measure the slope of this graph as well and transfer it onto the next graph, which is called a snap time graph. Measure the slope of a snap time graph, and you get a crackle time graph. And hopefully you can guess the last one. The slope of a crackle time graph is a pop time graph. I kid you not. You can Wikipedia that up. Okay, and you know, I think you can finish off the exercise on, I think, course pack page 5 for that one. Okay, now let's go and convert a VT graph into a DT graph, and yeah, we'll practice an AT graph as well. Okay, so anytime that you're going downwards, you're measuring the slope. Effectively, you're doing the derivative in calculus. Meanwhile, if you go backwards from the previous graph, then you're measuring the area underneath the graph, which is what an integral is. Did I say calculus or derivative? I hope I said derivative. Okay, yeah, when you go down this way, you're doing the derivative of that graph. Okay, so let's perform the integral of this velocity time graph. Now, if we don't know where we started, then that's why this is called a displacement time graph. All right. Meanwhile, if we notice that we started at exactly position 0, then it's a position time graph. Okay. Anyways, we start off at our initial reference point. From here, we just simply splice this up. You probably want to use reasonable splices. For example, if you splice it up into small sections like this, it'll take you forever to calculate it out. So that's why I'm not going to splice this into the whatever this is, the 1 second mark. All right. I'm going to splice this at 2 seconds. Reason for that is that I notice that I have a nice lovely triangle. All right, and with a nice lovely triangle, we know that the surface area of a triangle is equal to half base times height. So 2 units times 2 units is 4, divide that by 2, and we get 2. In fact, let me just add one more point for those that don't really know what's going on over here. Right, you're supposed to figure out the trends afterwards, and I know it's way too tempting to play connect the dots over here for your displacement time graph, but that can't be the case because your velocity started off at 0 and it gradually got faster and faster and faster and accelerated up to, in this case over here, if this is a 2, then 2 meters per second squared. Anytime that you accelerate, you should have a curve. All right, maybe from your perspective it will look like this. Okay, you'll have a curve that looks like this. It'll be a parabola opening upwards. To further prove that it'll be a parabola opening upwards, how about I just take a point right over here, okay, and then measure out the area of this. So 1 by 1 is 1 divided by 2, drops down to half. Hopefully that will give you a hint that this should start to look like that, and it does. Okay, the next part is that of a rectangle. In this case over here, because our velocity remains at 2 meters per second, we're experiencing uniform motion, or traveling at a constant velocity. So after 1 unit at a time, we've moved 2 meters per second, or sorry, 2 meters, and then after another second in time, we've advanced another 2 more meters. So yes, in grand total, this does add up to 4 blocks, and yes, we do have a rise of, whoa, I misdrew that. There you go, 4 blocks up to there. Take out your trusty ruler, slap it on your piece of paper, and go ahead and draw that. One thing I noticed on my curve over here is that my slope of my first curve was a little extreme because I shouldn't expect any kinks or cusps over here. All right, it should be a much more linear flow like that. There you go. That looks a whole lot better. I was just slightly off there, and you can see that I was. Okay, yeah, it should look rather smooth like that. However, there is an abrupt change right over here where I suddenly smack against the wall and my velocity drops to 0. And then yes, you will form a cusp on your graph and it'll look like this. In real life, this is impossible. Objects don't immediately stop. They need to decelerate. So if you zoom into here, you probably do see a curve. All right, but this is more of an exercise. And as a general exercise, we'll just accept that, you know, that's just the answer we get because this is the VT graph that we were given as our data collection. Okay, our velocity here, by the way, is at 0. So it remains stationary, and that's why we don't displace up here. Okay, we will remain at the same spot. Anytime that you have data beneath the velocity time graph, you're moving in the backwards direction. So now we're getting closer to our origin, at least in this diagram here. We see that we have a lovely triangle here. Half base times height divided by 2 will give us 1 unit. So it's going to be somewhere back there. Okay. And remember that you started off at 0 meters per second and you finished off at -1 meter per second. So this should be a parabola opening downwards and should look something like that. There you go. Okay. Now when you're doing this on a piece of paper, don't be shy. You can take your piece of paper, you can flip it around, right? It's very hard to draw, for example, an opening parabola opening upwards like this. Maybe if you arc your hand like this, it's easier to draw. But at the same time, too, you can also take the piece of paper, flip it 180, and then you'll be able to naturally arc it. I mean, when you submit in your test at the end, your teacher or professor has no idea how you held the piece of paper when you drew it, right? So you can orient it however you want so that you can artistically create nice curves, okay? And please don't slash, all right? So for example, my displacement time graph, don't go off doing something like this. That's a big no-no. Confidently draw that curve. Okay? All right. Next part is that we see that we have a rectangle that has negative area. How do we know the area is negative? Because time is positive, but my velocity is negative. Okay, positive times negative will give us negative area. With that negative area, we're still moving backwards. In this case over here, 2 units. Another way to do it is 1 unit back after 1 second and another unit back after another second. That's another way to figure that out. Okay. There you go. Okay, just to speed things up, I think we see things that are very similar now. All right, we know that this is -1 area, and this is still -1 area. Oh, still moving backwards. Oopsie daisy. All right, so now it should be a parabola that's looks like that. Okay, opening upwards to the left of the center. The last part is a parabola opening up vertex. That was the word I was thinking of. Opening up like that, and there we have it. There is our DT graph. Okay, the bottom part, I hope that's more straightforward. All we're doing is we're just measuring the slope. That has a slope of 1 unit throughout this entire time. Please don't freehand. Take out your ruler and carefully draw that out. Then we notice that the slopes over the next few seconds, the next 4 seconds, are at 0. Truth is that, yeah, during this guy over here, that is a negative slope to negative infinity, so you should have a vertical line there. Don't worry about it. We're not going to be that technical. In fact, as I said, it's impossible for velocities to go from 2 meters per second suddenly to 0. You need to have some form of deceleration in real life. Okay, but this is more of an exercise than anything else. We have a slope of -1/2. slope of 0, and a slope of positive 1/2 for the remainder of the journey. And if you feel compelled towards finishing it off by drawing these lines, it doesn't bother me. All right, and then we're good to go. That's how you convert a graph. I think there's a few questions on the right, and let's answer them before we finish off on today's adventure. Okay, first off, can you predict your position based upon just the VT graph? Remember how we said with the VT graph, it just tells you how much you've moved forwards or backwards. It doesn't tell you where you started. So no, you cannot predict the position unless if you know that you started at position 0. Okay, so that's the answer for number 3. Unless if you know that you started at position 0, you can't figure out where you're located just on a VT graph alone. After all, if I started my VT graph from right over here and started drawing everything and you didn't see any information over here, well, it doesn't necessarily mean that you started from up here. You could have started from over here and created that curve. All right. Actually, that's one more thing I want to point out is that if this was a position time graph, okay, if you start at position 0, this is the graph that you get. If you start off at position number 2, then you get something that looks, I'm just sketching it out like that. And if you start off at position number 4, and I hope you get the idea. Okay, and these are known as a family of curves, and that's one of the problems whenever you do the integral or the area underneath the graph. You don't know what your y-intercept is at the beginning, so all you know is the trend of the graph. You don't really know where it started. Okay, so for those that are taking calculus at the same time, hopefully you understood what I just talked about. Number 4, can you predict your initial velocity based upon just an acceleration time graph? The same is true. All right, if I just take my acceleration time graph from, let's say, right over here, well, even though my acceleration is at 0 here, you can see that I'm already moving forwards at 2 meters per second. So by blatantly looking at acceleration time graph, you have no idea how fast or how slow you're moving. All you know is whether if the velocity is being added on or being subtracted on. You can't even tell if it's increasing or decreasing. All right, and that's the thing about an AT graph. You can only tell if you're adding to that measurement or you're subtracting. All right, anytime it's above the time graph, then you're adding your velocity, because you could be adding to a negative velocity initially, so you're decelerating, or you could be adding to a positive velocity, so now you're positively accelerating. Okay, what does the area underneath a position time graph represent? Okay, let's start off with this. Area of an AT graph, this tells you your change in velocity. Whew, I gave away question number 6. Okay, what about the area underneath the VT graph? Well, that tells you your change in position. What does that mean? Well, change in position really is your displacement. Hope you can link those worlds together. So if you were to try to find out the area underneath the displacement graph to go to the previous graph, then now you have a change in what? And it doesn't make any sense. All right. Another way to prove this, that it doesn't make any sense, is by looking at the units. Okay. For example, if you're trying to find out the area of this, you'll be multiplying the base by its height. So the base is measured in seconds and the height is measured in meters per second squared. And if you calculate that out, that works out to meters per second, which is the definition of change in velocity. You can do it the same with the velocity time graph. Okay, I just want to use a rectangle just because it's easier. All right, so we have our base of whatever seconds and our height measured in meters per second. That gives us meters. That is the correct unit for displacement or change in position. Now, if you try to find out the area underneath the displacement time graph, then you have a base of seconds and a height of meters. And that gives you meters times seconds. There is no measurement that's measured in meters seconds. All right, it's a meaningless unit. So there is no meaning underneath an area. No meaning. No meaning of an area underneath the position time graph. All right, and I think that's all the questions we have here. So continue on with your course pack and make sure you start to memorize the 5 kinematic equations. All right, because when it comes to test time, those 5 formulas will not be given to you. You're expected to know it by now, all right, by grade 12. So tonight, go through graph conversion and start memorizing from your notes from back in grade 11. I'll see you in tomorrow's episode. Bye now.